Okay. We are going to begin with exponential growth and decay, which is just, it's a new topic. Didn't really do anything on that. Nothing really to quiz you on because I didn't give any new material. Yeah, so you guys should have seen your report cards. Did everyone get it? Okay, so you have to email me and let me know that you didn't get yours. I'll give the test back afterwards. And then same rules apply. Now it's more important than ever that you talk to me if you did poorly. Because it really depends. I kind of mentioned that maybe like a 50 mark. If you got below a 50, that's kind of bad. But it depends. It would depend on a lot of things. So if you did like really bad on the first test, like you got like in the teens or 10, and then you jump to a 50, that's actually pretty good. And it might be worth you staying, but it would depend individually. So you should talk to me. Based on how much you improve versus on where you are, it will make a difference. And if you continue improving the way you've done, then you might stay. But anyway, you guys can talk to me afterwards. I probably won't have too much time tonight after class, so to get these back, take them home, look them over. If you think I robbed you any points or anything, just mark it out, point it out to me. And see me tomorrow would be probably best, as soon as possible. If not, see me on Wednesday, because Thursday is the last day to drop. If you guys didn't know. So yeah, I'll give you after class. I don't want people paying attention, going through their tests while I'm teaching. I want you to pay attention to this right now. So this handout is one of the handouts I gave last time, Exponential Growth and Decay. Hopefully you have it. If not, it's also on the class webpage, so you can get the handout for this and the next one. Conceptually, there's not much we want to do here. It's basically, I'm just going to give you some formulas, teach you how to use them. The formulas that we talk about here, actually when you go to the next class, Math 209, you'll learn where they come from. They're going to derive them for you and show you why it had to be this way. But for now, for exponential growth and decay in 205, you just need to know the formulas that apply and plug in the numbers in the right places. So to summarize the things you need to know, so there are two things. The forms are actually pretty similar between these two. So for growth, it's important that you know the following. There's one equation that looks like this. So P of t, and I just write P if I'm lazy, but it's actually a function of time, right? This is the amount of a quantity current amount of a quantity that grows exponentially, or another interpretation that we can give this is it's the balance on a bank account where interest is compounded continuously. Which would never happen in the real world. No one's going to pay you interest compounding continuously, but there are virtues to looking at this model. So, especially in small time gaps. Right. So P I'm just calling, I'm using a function to track something that grows exponentially. Growing exponentially just means it grows by a percentage of its current size per unit time. So I could tell you, oh, something grows by 50% of its current size, which means if I start with 100, after some unit time, I have 150, right? Because it takes 50% of 100 and adds to that 150. And then after that same time has passed, it takes 50% of 150 and adds to that. right? So if you have something that keeps adding a percentage of its current amount to itself per unit time, you say it grows exponentially. A similar thing happens if you have a bank account where the interest is compounded continuously. It grows the same sort of way. Right? This is called exponential growth. So there's one equation that governs this is called a differential equation. This is definitely something that's out of the scope of this class. Next class you'll see it. But that is the equation. This is called a differential equation. So that's a phrase that you might see in a problem here, where they'll say, write down the differential equation. They're talking about writing down this equation here. If you have something that tells you what the size is in original, this is when time equals 0, or initially, and they would give you a value, which we usually describe with this is the value. Okay, this equation is called the initial condition. So that's one set of equations that you'll need to know. Usually you'll say these two things together, right? So you have a differential equation that describes the rate of change of p. This is telling you what p prime is equal to. P prime is equal to some percentage growth times itself. It's telling you what you're adding to yourself after some unit time. This equation is an equation that tells you where it starts. That's called a differential equation. This is called an initial condition. Right? So this is, number 2 is the formula for P. i.e., it's called the solution to the differential equation above. That is P is equal to P naught e to the RT. The PERT formula is how I remember it. That's just how I remember it, because PERT is the name of a shampoo that was really famous when I was growing up. So just remember PERT, P e to the RT, right? This is an equation that describes how this quantity will grow, right? So R, in this case, here, P I already told you what that was. So P equals the current amount at time t, right? When you know the quantity is growing exponentially, which usually they will tell you in the problem. P naught is the initial amount. That's the amount you had in the beginning. R is called the growth constant. Or it's sometimes called the relative growth rate. It's very important that you remember that, because a lot of times students mix that up with P prime, which is, it's called the rate of growth. Or the growth rate. They use the same words, but the order and how you combine them is very different. Right? So there's a difference between the growth rate and the relative growth rate, or the rate of growth and the growth constant. Do not mix those up. Right? If they say rate of growth or the growth rate or how fast is P changing, they're talking about P prime. If they talk about the growth constant or the relative growth rate, relative being the operative word, they're talking about the little r, the power in the e. So that's an important point, an important distinction to make. So make sure you don't mix up those two. Right, so in a word problem, when they use a certain terminology, you need to know which one they're talking about. In the case of the bank balance, interpretation, R is the interest rate a decimal percentage. So for example, if they tell you that you have a 5% interest rate, then that means your R would be 0.05. Right? So you go in this formula and you'll plug in R equals 0.05. Okay. Otherwise, the R you'd have to figure out. Otherwise, you figure out R given some extra information. One useful equation, it's useful because it's something that they ask about all the time, and I probably ask about it, I'm asking such a problem, is a third equation that says the doubling time. This is the time it takes t to double in size. Right? So if I start with 100, how long will it take me to get to 200? Or if I start with 300, how long will it take to get me to 600? That's called the doubling time, and it turns out that that is equal to ln2 over r. So that ends up being a useful formula. Because they like to ask that question. How long will it take to double your money if you have a 5%, if you have a bank account growing at 5% compounding continuously, right? You can just plug into this equation. Once you figure out the R, you just plug in 0.05 here. ln2 over 0.05 is how long it will take to double your money. So it's often a very useful equation. Why? If we have P equals P naught e to the RT, right? So we want T such that, what would we want P equal to? Right, if I want to look for when it's going to double.
ln2 over.
Remember, P naught is the initial amount. That's how much we start with. So if I want to figure out when it's taken to double, what would I want to look for when the P is? I'm looking for the time to double. I know P naught is what I start with. It's going to be some number. Huh?
P0 is E.
P0 is the original amount. It's some number. It could be 100, it could be 500, it could be 125, it could be whatever. 2 P0. Right? Double whatever I started with. Right? Which means you end up with this equation. 2 P naught equals P naught e to the RT, and you want to solve for time. Divide both sides by P naught. How do I solve for T? ln, right? You use ln to get rid of e. And so you have ln2 is equal to RT. And in which case, if you solve for T now, you get T is equal to ln2 over R. Right? So the time to double will be ln2 over R. And that's why. You're just using that equation to answer it. But it's nice to just know this as a shortcut, so you don't have to go through this all the time. That's just something you know. But it stands to reason here that you can actually figure out when it's going to be any multiple of what the original was, right? So if I say, what's the time to triple? You just put 3 P naught here. You'd end up with a 3 here, so it would be ln3 over R. What's the time to quadruple? ln4 over R. Time to have 7 times what you start with, ln7 over R. Right? But time to double is a common one, so ln2 over R is just something you should know. So as I said in the next class, you'll actually derive this derive these equations from scratch, and you'll see where they come from. For now, I'm just giving you the formulas, and we're just going to use them. And these are all the formulas that you need to know. For growth. For decay, if I'm looking at decay, there's just one minor difference. Now, decay means things are getting smaller, right? So P equals current amount of a quantity that decreases exponentially. There are a lot of things that behave this way. Radioactive substances usually decay exponentially. So you have then, these are the following equations. Then your differential equation will look like minus RP, because you have a negative rate. That means decreasing, right? Similarly, you can have P0 equals P0. So this is the differential equation. And this is the initial condition. Secondly, the solution would look like the following. P is equal to P naught e to the minus RT. Is the equation that describes P. 3. The important equation here is the one for half-life. If you're into science, you'll hear the term half-life all the time, right? And again, this is going to be ln 2 over r. This is the time it takes to have half of what you started with. So if I start with 10 grams, how long will it take me to get to 5 grams? That time lapse is called the half-life, right? And it's equal to ln 2 over r, which seems to be the same thing for exponential growth. Well, how does that work? Why? Well, similarly, we want, in this case, P to be 1/2 of what we started with. So we get 1/2 P naught equals P naught e to the minus RT. Divide both sides by P naught. Take ln of both sides. And this means that my time would be ln of 1/2 divided by minus r. Why is that the same as this?
Because ln of 1/2 is negative ln of 2.
Right, ln of 1/2 is negative ln of 2. There are a couple ways you can see this, by the way. The negatives cancel, get ln of 2 over r. So you can see that by ln of 1/2, you can think of this as ln of 2 to the minus 1, in which case you can bring the power down. You get ln of 2. You can also think of ln as 1/2 of ln of 1 minus ln of 2 by another log rule. Ln of 1 is 0, and so you get minus ln 2. So there are tons of ways you can see that ln of 1/2 is minus ln 2, and you get ln 2 over r again. So the only difference between growth and decay is, of course, growth gets bigger, decay gets smaller. So things like bacteria's populations, money in a bank account that's gaining interest would fall under growth, and things like radioactive decay or some population that's dying rapidly will fall under exponential decay. As for your formulas, the only thing that's going to be different is you're going to put a negative in front of the r's. But the half-life is still just ln 2.
So,
Yes.
what about that negative r? This is going to be ln over positive r
Yeah, ln over the positive.
for both?
Yes, half-life is this.
Okay.
Now let's do some examples. The examples are on the second and third page. So some of these were taken directly from finals, so they'll look exactly like that on a test. Start with the first example. So you go to the second page. This first example is actually from final spring 2009. There's problem 4 on that final. Okay. So this is how the problem is going to look. So we're going to give you some information to talk about the quantity we're talking about. Then they're going to ask you some questions, which once you've set up these equations, you can answer anything, right? So let P of T be a population of colony of bacteria. At 11 a.m. there are 60. At 3 p.m. there are 350. Assume exponential growth. So they're going to tell you, okay, exponential growth is what you're doing, right? So here, now we need to figure out these equations, right? In part A, it says we need to find P of T. Right? So we know here, because they told me it's exponential growth, I know that P is going to be something like this, P naught e to the RT, right? Now the thing is, the P naught and the R I need to figure out, right? Those are constants that I need to plug in. So now, how do we find those? Ideas. Turns out here we can know what P naught is right away. What is that? 60, right? So remember the definition of P naught in our formulas is the initial amount, what you start with, right? So here it says we start at 11 a.m. with 60. So P naught I will take to be 60. And 11 a.m. I will take to be time equals 0, right? So I'm taking 11 a.m. to be the beginning. At that beginning, I have 60 individuals in this population of bacteria, right? Okay. So I know P naught is 60, that's fine. So now, I already know the P naught, now I need to focus on finding that R. So what other information do I have here? I know at 3 p.m. my P is 350. Right? The current amount is 350 at 3 p.m. What's 3 p.m. in terms of our time? 4. 3 p.m. is T equals 4. Right? Notice that here I'm measuring time in hours. Units is always going to be important as well. Right? So once we decide we're measuring time in hours, that's going to be T equals 4. So at T equals 0, I have 60. At T equals 4, I have 350. Okay? So how do I use that information to get to R? What do you think?
Substitute.
Okay, so what am I going to get?
R with 350
So P is 350.
equals 60.
P naught is 60.
E
E is E.
to the R.
The R I don't actually know.
And to the 4.
T is 4. So that's an equation where R is the only unknown. I can solve for the R. How do I do that? Divide by 60. So 350 divided by 60 equals E to the 4R. Then ln both sides to get rid of that exponential. So I have ln of 35 over 6 equals 4R, which means my R is ln of 35 over 6 divided by 4, and you cannot divide this 4 into that. That's as simple as you can get. Which means my P is equal to 60 E to the ln of 35 over 6 over 4 times T. That's part A. You can simplify that, but that's fine. I don't care if you simplify that. Now you move on to part B. What is the size of the population at T equals 4 p.m.? How would I figure that out? What? What are they asking for in part B? They want the size. So who's the who here represents population size? P. So what we want is we want P. When do we want P?
4 p.m.
At 4 p.m.
When T equals 4 p.m. What is 4 p.m. is?
5 hours.
Right, so we start at 11, T is time in hours, so 4 p.m. means T is 5. So basically they said we want P when T is 5. That's basically what part B is about. And so all you pretty much do is you go to P and plug in T equals 5. That's it. Part C. When will the population reach 2,000? What is that asking us for?
Within the time.
Time, right? It says when, right? So this is what T such that
So that P is equal to 2.
such that the P is equal to 2,000, right? That's the population size. So you told me the population size is 2,000. Tell me when means they are asking for T, right? So this means I'm just going to plug in 2,000 here. And I need to solve for that time. Okay, how do I get it? Divided by 60. Excuse me, e to the ln of 35 over 6 over 4 t. Continue over here. And I can go further. That becomes 100 over 3. Ln of 35 over 6 over 4 t. How do I solve for t? Ln becomes repetitive after a while. Ln of 35 over 6 over 4t. And now to solve for t, just divide by this guy. Ln of 100 over 3. Multiply both sides by 4, then divide both sides by ln of 35 over 6. And that's your time. Any questions on that? Let's pretty much run through it again. If you look at fall 09, problem 4, it's pretty much exactly the same question. So let's just run through this again. Pizza population of a colony of bacteria. At 10 a.m. there are 50. At 3 p.m. there are 350. Assume exponential growth. Find P of t and simplify. So here, I know that P naught is equal to 50. I know that t equals 0 at 10 a.m. I know that when t equals, so between 10 and 3, how many hours elapsed?
5.
When t equals 5, my p is equal to 350. This means 350 is equal to 50 e to the r times 5, which means 7 is equal to e to the 5r. Then you're going to ln both sides. of 7 is equal to 5r, which means that your r is ln of 7 over 5, which means your p is equal to 50 e to the ln of 7 over 5 times t. Then you move on to part B, which says, what is the size of the population at 4 p.m.? So when t equals, since I started at 10 a.m., 4 p.m. would be 6 hours away, right? So when t equals 6, as my p is equal to 50 e to the ln of 7 over 5 times 6. That's the answer for part B. C, when will the population reach 1500? So here we want t such that p is equal to 1500, which means 1500 is going to be 50 e to the ln of 7 over 5t. I don't want to solve for t, which means I would get, what is that going to be? 30 is equal to e to the ln of 7 over 5t. So ln both sides. And so I have ln of 30 is equal to ln of 7 over 5t. And that's questions? Some of that you'll get with practice, so let's do a couple more examples here. Do problem 8, spring 2009. Dosage of 3 milligrams of radioactive iodine is administered for some forms of thyroid cancer. The half-life of that guy is 8 days. If the maximum permissible level of iodine in the thyroid is 5 milligrams, what is the minimum number of days before the second dosage of 3 milligrams can be given? Assume the iodine is totally absorbed by the body and not excreted. Okay. So the question is, when do we give the next dosage so we don't kill the first patient? So one hint that you're under radioactive growth, you're under exponential growth and decay is the fact that they use the term radioactive. So they say radioactive. That actually means exponential decay. Same thing when you see the phrase half-life, you would think exponential decay. So these are two, when you're reading this problem, right? So remember on the final, you're gonna have like everything, right? You need to know which topic are you reading about, right? So things like radioactive, half-life, exponential, the word exponential growth or something like that. These are things that hint towards you that you're doing this topic. Okay, so those two words will tell me that this is an exponential decay problem. Okay, so I know what formula governs that guy. P is equal to P naught e to the minus RT is going to be the guy I'm going to want to use, right? Where P is the current level of iodine. P naught is the initial amount of iodine. R is going to be the growth constant, which is going to tell me how fast that thing is decreasing. T is time. Okay. So now in order to answer this question, I need to fill in what is P naught and what is R. Okay. So how do I figure that out? What is P naught? 3, right? You inject the patient with 3 milligrams. So now you start the stopwatch. He now has 3 milligrams of iodine in his blood. So we know that P naught is 3. How would I figure out the R? Well, there must be some information in the question. So what information would we use to figure out the R?
From the half-life?
They told us about the half-life. They said the half-life of this substance is 8 days. So right now I know that the half-life is 8 days. How does that help me find R?
P is equal to P0 over 2, so we can
Will take 16 days for all of it to be.
Come again?
But then it'll take twice as much for the work to be done.
Not really.
We can plug it into LN2R.
Because there's something wrong with that one. Because I think you're thinking of linear decay instead of exponential decay. But we'll talk about that later. Half-life is ln2 over r. That was a formula that we had. So I have this equation. I can solve for r from that. So this means that r is actually just ln2 over 8. Right? So this would mean that my p is equal to 3 e to the ln2 over 8t. Remember, there's a negative sign now because it's decay.
So I have a question. Whenever
Yes.
we get half-life, we have to do that?
I would. You don't have to, but it's pretty much the easiest thing.
Okay.
Yeah. You could solve for it. You could have something like, you know that p is equal to 3e to the minus rt. You know half of 3 is going to be over here. You put 3 over 2. And you plug in t equals 8. And if you solve that for r, you'll get this. But why go through all the work? You know, I'm not giving this equation. Right? Half-life is a very common way to describe radioactive substances. Right? So odds are, if there's something talking about exponential decay, they're going to mention the half-life. And if they mention that, you already have an equation set up to deal with that, so you just use it. So I know this is the equation that's going to make this thing, that's governing the amount of iodine. The current amount of iodine in the bloodstream is given by that equation. Okay, so now, how do we make sure we don't kill this patient?
Measure count.
What did we say? Right, the maximum amount they can have in their bloodstream is 5 milligrams, right? Now we gave them 3 milligrams, right? So how long of a time can I wait before I give them another shot of 3 milligrams?
P is 2.
When P is 2. We have to wait till most P equals 2 to give another 3 milligram shot. Right? So I give them 3 milligrams in the bloodstream. Now it's the body's absorbing this, so it's decreasing, right? But how do I know before I can give him another shot? Well, he can't have more than 5, which means I cannot give him another shot of 3 until what's in his bloodstream is 2, right? So all I need to do is figure out when will the amount decay to 2, and that's at least as long as I have to wait to give him another 3 milligram shot. Right? So this just means you plug in p equals 2. And I'm going to solve for that time. So then divide by 3. Ln both sides. Then divide by the coefficient of t. And that is my t. That's how long I have to wait before I can give him another shot. By the way, we need to make sure our answer makes sense. This negative sign might bother some of you, but that's easily dealt with if you just remember that ln of 2/3 is actually negative. Right? Because we remembered, of course we remember, the graph of the logarithm. That's at 1. Once you're bigger than 1, your ln is positive, but once you're smaller than 1, your ln is negative. So 2/3 will be here, so your ln of 2/3 is actually a negative value, so this negative sign is okay. So if we're double checking our work, you just say, oh, that's word for a negative, and then you remember the graph of ln, and you're like, no, it's fine. Okay, so that problem actually required a little bit of interpretation. To figure out that p equals 2 is what you want to set it to. You have to do a little bit of arithmetic there, but it wasn't such a bad idea. So that was one with half-life. Let's try fall 2009. Let's do problem 11. So this is one with a bank account. So here it says a bank pays 5% interest compounded continuously. That phrase, compounded continuously, is one of our important phrases that we look out for. Compounded continuously means exponential growth, which means that all the formulas I said at the beginning of class apply to this thing. Right? So now it says a bank pays 5% interest compounded continuously. Suppose you make a deposit of $4,000 in the account. A, write a differential equation together with an initial condition whose solution gives the amount in your account at any future time. So I know the differential equation and initial condition. I know that p prime is equal to rp, and p of 0 is equal to p naught. So there are two things I need to figure out here. Let's see. So remember, r is a constant. I need to know what that value is. P naught is also a constant. I need to know what that value is. So in this case, what is r?
0.0.
0.05, because they told me it's 5% interest rate. So it's just 0.05 p, and p of 0 is, what's the balance in the beginning?
4,000.
4,000. That's how much I initially deposited. That's your answer.
That's good.
This guy is called the differential equation. This guy is called the initial condition. It's just a matter of memorizing those formulas and plugging in the guts. Right? So in those formulas, you have to remember the r, the p, and the r and the p naught are the constants you have to find. Right? It means nothing if you don't know those numbers. So you have to use the information that's given to figure out those numbers. And that's it for part A. For part B, at what rate is your account increasing when the principal reaches 6,000? So now you need to remember when they ask about rate, they're talking about p prime. Right? So we want p prime when p equals 6,000. Since p prime is equal to r times p, and I know what r is, and now I know what p is, I just plug them in. What's that? This is way too easy. Didn't really have to do anything. Okay, maybe we have to do something. How long will it take the principal to reach 5,000? How about that?
You're gonna use exponential growth?
Right.
equation?
I know that exactly. So I know that that's the equation I want to use. The P naught I know, and the R I know. So I know I'm using P is equal to 4,000 e to the 0.05 t. So how long will it take to reach 5,000? I want the current balance to be 5,000, so I'm just going to put in 5,000 there. So now, of course, you divide both sides by 4,000. You get 5 over 4 is equal to e to the 0.05 t. So then both sides. And that's how. And the rest of these are pretty similar. They're not going to be much, I wouldn't give you much different either. People always say my problems are different from the actual problems. Look, I disagree, but whatever. So if I was writing this problem to put on a test, what would I write it to look like? Okay? So the base, the context in which I would write, I make it look like Spring 09, problem 4. I wouldn't give you a problem like problem 8. Or I could do something like fall 09, problem 11 in the second part. I think fall 10 is also a nice one to use. Problem 4. In fact, yeah, that's actually a good one. I'd probably write something exactly like fall 10 problem 4. Because that one asks you about everything. It asks you about the differential equation, asks you about finding P of t and simplifying, asks you to find the amount of substance remaining after t equals 75, and then it gives you the amount and asks you to find the time. So this is one problem that literally asks you how to find everything. So, except here in part A, I also ask you for the initial condition. And I would probably also add a part E, saying something like, what is the rate of growth when time equals something, maybe like time equals 20 years, as an example. In which case you just use P prime equals RP of 20. Right, so you just plug in P. Once you find the P, you plug in 20 into that, multiply by the R, that's it. In which case the R we already know here, it's ln 2 over 30 times P of 20, which is going to look like ln 2 over 30 times the initial amount is 200 e to the minus r times t. I plug in 20 here. And that would be the answer to that problem. So that's what I would ask you in the test. In the final, I'd pretty much ask you exactly like fall 10. In a test, I'd add a part E. So you can imagine fall 2010. That's a nice template, I think. Right. So I could ask you the same kinds of questions, except I do exponential growth instead. Or I can ask you the same kind of question, except I pretend it's a bank balance. But they're all kind of the same thing. They all use the same kind of equations. So we'll stop there. Practice the others on your own. Maybe I can just put them on a quiz to see if you guys actually did them correctly. Because students are like, yeah, I'll go home and practice on my own. It's like, okay. Yeah, Jhevon, yeah, we'll go practice. Give them exactly the same problem. I've never seen that before. Your problems are so hard. Okay, moving on. Related rates. There's really nothing else to teach for exponential growth. It's just a matter of knowing those equations and knowing how to read the problems to plug in the right information. Related rates, though, is a little bit more involved, so I want to get started on that early. We might not finish it by the end of class, but we'll finish it by the next class. But let's get started. This one is going to be a little bit harder to wrap our minds around. Let's get into it. So hopefully you have the other handout, related rates. If you don't have it, it's on the class webpage, so you can download that later. But for now, we're going to move on. So related rates, as the name suggests, it's about quantities where their rates are related. Talks about several quantities that are related. Right? Of course, it's math. So related means there's an equation that connects them. There's an equation that connects them. So in math, that's what related means. There's a function that connects the two variables, or more than two variables. So when two quantities are related, turns out this means their rates are related. How do you figure out that their rates are related? Well, implicit differentiation. So related rates is just an application of implicit differentiation. Rate, the word rate in language in general, it kind of means time is the independent variable. So those are just some conceptual things. Let's just first talk about how do you know that you're looking at a related rates problem. There's a very specific way that we like to ask the problems here. So remember, by the time you get to the final, we're going to be doing so many applications. There are going to be so many different kinds of word problems. You really need to be able to look at a word problem and know, oh, is this exponential growth? Is it related rates? Is it optimization? Is it something else? Right? So I told you how to recognize some of these exponential growths. You see phrases like compounded continuously, radioactive. You know, it might actually mention the word this follows exponential growth. Right? How do you know when you're looking at a related rates problem? Right? So one. The problem will describe two or more related quantities. And it will tell you the rate of change of one or several of them. Right? And two, it will ask for another rate. Right? So when I tell you, oh, x and y are two quantities that are connected this way, but your x is changing at this rate, what rate is the y changing at? Right? That's like a template for related rates. Right? They're going to tell you about things that are connected. Could be an x and a y, or an x and a y or a z, or they might even just use words. It relates to quantities, right? But they'll tell you that there are things that are related, and then they'll give you a rate of change of something. They'll tell you how fast one of them is changing, or how fast two of them are changing. And then it's going to ask you, how fast is the other one changing? Right? That's a related rates problem. That's how you know when you're reading this word problem, it's a related rates problem. Now, once you figure out that it's a related rates problem, half your work is done. Maybe 33% of your work is done. Because once you know it's a related rates problem, go through the 6 steps. 6 steps in the handout in that order. Some steps may be done for you in the problem. They might just give you the answer to a step that you need to figure out, but you'll still, in that order, check them out. So I gave you here 6 steps to solving a related rates problem. That works on every single related rates problem. Every related rates problem you will ever see in this class. These are the 6 steps you will go through to solve the problem. So of course that would mean you need to know the steps. Or you can kind of wing it and figure it out. But I do not recommend that. You'd have to be very comfortable with math to just be like, oh yeah, I can see where this is going. We're going to just follow these steps. If you do enough of them, you'll actually get an intuitive feel for it, why you had to do it that way. But for now, just to get this out there, these 6 steps, any related rates problems, you kill it with this. Okay. Okay, so let's go through the problems. Step 1, read the problem carefully. That is actually very important. So read the problem, make sure you understand what's going on. Okay. 2, if possible or necessary, draw a diagram. Right? I'll come back to why we want to draw a diagram. It's very important, though, that when you draw the diagram, label quantities that are changing with variables and quantities that are not changing with constants. There are a lot of mistakes that can happen when students don't do that. Anything that's changing, label with a variable. Anything that's not changing, label with a constant. And you want to think of your variables as functions of time. The third thing you're going to want to do is you're going to write down what information you're given, right? Whatever the problem tells you, like if it tells you a rate, write that rate down, right? Write down what it is using the variables that you labeled in your diagram, right? Then you're going to write down what you want to find, right? So you're going to write down, this is what I have, this is what I want, right? You need to set a goal for yourself because at the end of the day, you're going to need to answer that goal. Okay. Now, in step 4, the 4th step we're going to do is you're going to set up an equation that relates all these variables that are in your diagram. Which means the whole point of your drawing a diagram is to figure out what equation you want to use, right? Because the diagram will kind of tell you what equation you might want to do, right? So if you know if your diagram is a rectangle and they're talking about area, then you're just going to do length times width. That's the formula that you're going to come up with. If your diagram is a triangle, then you come up with another formula, right? So the form that you're setting up in step 4 connects to your diagram. That being said, if they give you an equation, you don't need to draw a diagram because the whole reason you draw a diagram is to set up an equation. So if they gave you the equation, you can kind of skip step 2, right? But you still would go in that order, right? You just realize, oh, I don't need a diagram here, right? So you draw a diagram to figure out how you want to set up an equation, right? Once you set up the equation, what you're going to do, and I flesh out a lot more in the handout, the things that you should consider in each step. Once you set up that equation, you are going to differentiate it implicitly with respect to time, right? Which means all your variables are functions of t. So if you see an x and you differentiate it, you have to put a dx dt on it. See a y, dy dt. See a z, dz dt. Any variable, it has to be with respect to t that you're differentiating, right? Then problem 6 is plug in what you know, which is what you wrote down in step 3, and solve for what you don't know, right? And as you can see here, there's a caveat to that. Sometimes you won't have enough things that you know to plug into that equation, so what you do is go back to the equation you set up in 4, solve for anyone that you don't know already, then come back to step 6 and plug them back in, right? That might happen sometimes. But at the end of the day, once you do that, you want to answer the question that they asked you, which is why you need to write down that goal. This is what I'm looking for. You make sure at the end of this whole process, you tell them the answer that they asked you for, right? And those are the 6 steps. It'll always be those 6 steps, right? So that's really abstract. Let's actually try some problems though. Let's start with example 3, because that's similar to a bonus problem that I put on the test, and I think it was on the quiz as well. So I think it's a nice problem. And then we'll do something. Okay. A 15-foot ladder was resting against a vertical wall. Okay? Suddenly, and without warning, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. At what rate is the top of the ladder sliding down a wall when the foot of the ladder is 9 feet from the wall? So you read that on a final. How do you know it's a related rates problem? They describe a situation to you, they tell you a rate of change of something, and then they ask you for another rate of change, right? That means it's a related rates problem, right? So here's the situation. There's a 15-foot ladder lying against the wall. The foot slides away at a certain rate that you're given. You want to figure out another rate, right? So, step 1, read the problem carefully. Make sure you know what's going on. Step 2, what we're going to do, we're going to draw a diagram. Kind of draw a diagram that describes this situation. What do you think it would look like here?
Like a triangle.
It's actually going to be a triangle, right? There's a vertical wall, right? So here's the wall. Here's the ground. And here's the ladder leaning against the wall. Now from that, you can realize that what you're actually seeing here is like a triangle. Right? So that's what's going on. Now, remember when we set up our diagram, what we're going to do. We're going to label things that are changing with variables and things that are not changing with constants. This guy here is the ladder. Is the length of the ladder changing? No, it's always going to be 15 feet. So I'm going to label this line 15. It is not changing. It will always be 15. I'm going to label it 15. I label it with a constant because it is constant. Now, this line here represents the distance the foot of the ladder is from the wall. Is that changing?
Yes.
Yes, because I told you that the foot of the wall is sliding away. So this distance here is getting bigger. It's actually changing. So that length here I'm going to label with a variable. Let's call that x. Now, you can imagine as this is sliding away, this would be sliding down, right? Which means that this length here is also changing. It's getting smaller. So this length here I will also label with a variable, call it y. And that is step 2. So I read the problem very carefully so I can figure out what kind of situation is going on. By reading the problem, I can figure out a diagram that describes the problem. I will label that diagram. Anything that's a constant, I will label it with a number. Anything that's changing, I will label it with a variable. Step 3, I'm going to write down what do I know and what do I want to find. All right, so here, what do we know? What do we want? So here it says, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. So I actually know the rate at which this thing is changing, right? The x, right? That's measuring how far the foot of the ladder is away from the wall. X is that distance. And I actually know how much that distance is changing from. So what I know is dx dt. I know it's actually what? 2. In particular, it's a plus 2. Plus because, why is it a plus?
Because it's getting bigger.
Because it's getting bigger. X is increasing. Right? Now, I could have actually the same kind of situation, but I said the foot of the ladder is going towards the wall. In that case, the x would be getting smaller, and I would put a minus 2 instead of a plus 2. So the sign here actually is important, right? Which is why reading is actually important, right? You need to read to know what signs you're giving to these rates, right? So I need to read and understand that my x is getting bigger, not smaller, and so the rate is going to be a positive change, not a negative one. Okay. So that's what I know. What do I want, right? It's usually going to be with what they want to find. At what rate is the top of the ladder sliding down the wall when the foot is 9 feet from the wall? Right? So I need to know at what rate is this thing changing, right? That's the top of the ladder sliding down the wall. So what they're actually asking me what I want is dy dt. When do I want it? Now. No. I want it when x is 9, right? Is that what they said? Right.
When y? Is it the same?
No. It says, at what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall?
Oh,
The
okay.
foot of the ladder is here, right? So it's describing me the x distance. Okay? So this is the rate I know, and they're asking me to find this rate at this, in that situation, right? So that's what I know, that's what I want. Okay, so I know at the end of the day what I need to tell them as the answer. Dy dt equals blah when x equals 9. That would be my answer. Okay, so I know where I'm headed. So step 1, read the problem. By reading it, I could figure out this is the diagram. And also by reading it, I know that that's the rate, this is what I want. So now comes step 4. What is step 4 now? The equation, right? I come up with an equation that relates these guys, right? Now usually, if this is the kind of problem where you'd set up a diagram for it, the diagram itself is going to tell you what equation you should use. What equation do you think we should use with this diagram? Pythagoras' theorem. Notice that it is a right-angled triangle because it's a vertical wall. You're assuming the ground is horizontal. So in this case, I would use Pythagoras' theorem, which tells me what?
15 squared is equal to y squared plus x squared.
Exactly. X squared plus y squared is 15 squared. Right? Sum of the square of the two sides is equal to the square of the hypotenuse. That is Pythagoras' theorem. So now I figured out this diagram. I use that diagram to tell me what equation I want to set up. Pythagoras' theorem is something that would relate all the sides in a right angle triangle. So this is the equation that relates all my variables. Step 5. Differentiate with respect to t. So I'm just going to go through this and implicitly differentiate, right? Which just means I differentiate and by the chain rule I multiply by the primes, right? Sorry, this is 2x times dx dt. Because I'm not thinking of x as just a variable, it's a function of time, right? So I have to multiply by its derivative. Plus 2y dy dt equals 0. Right? This is one of the reasons why you want to label things with constant when they should be constants. Because if I've seen students who would label this with a variable, and they put a variable here, and they differentiate, they get 2 times that variable times the prime, and they forget that that prime is 0 because it's a constant, it's not changing. And they plug in random numbers and get a whole new equation, right? So make sure you label things as a constant so you know that that's a 0, right? It's not something you have to worry about. Now, that's step 5. Now we go to step 6. It's time to start plugging things in to figure out what I want to find. Right? Now, what do I want? I want dy dt, right? Which means here's my dy dt. Which means what I want to do now is I want to plug in values for all these guys except dy dt. Right? Now I know what I want the x to be, that's 9. I know what the dx dt is, that's 2. Turns out I don't know what that y is. How do we figure it out? Go back to this equation, right? Because this guy, if I plug in x equals 9, I'd be able to solve for y. Right? So when you get to step 6 and you want to start plugging things in, if anything is missing, go back to step 4, because that's the equation that relates everything. Right? So you'll plug in things that you know into step 4, figure out what you need to find here, then come back to step 6 and plug it in. So, how do we find that guy? So now, notice that we need y here. So what I'm going to do is I'm going to go to 4, and I'm actually going to plug in stuff to figure out that y. So I know that 9 squared plus y squared equals 15 squared. So y equals what here? Sure, which is what? You're working too hard. It's 12. How do I know it's 12? And how would I know that without finding 15 squared and 9 squared? Triple. Huh? It's a Pythagorean triple. So, another thing you need to remember from algebra are Pythagorean triples. Right? It's a 3, 4, 5 triangle. Pythagorean triples. There are really only 2 in 205 that they test you on. There's what's called the 3, 4, 5 triangle. Right? So if you have a right triangle and the hypotenuse is 5, one side is 3, the other side must be 4. Right? But one side is 4, the other side must be 3. Right? These are numbers that always come together in a right angle triangle. Right? So if you know any of these 2, if the hypotenuse is the 5 and you know any of these 2, the other one must be the other number. Right? So if I have a right triangle where the leg is 4 and one leg is 3, the hypotenuse must be 5. If I know one leg is 4, the hypotenuse is 5, the other one must be 3, and so on and so forth. And it turns out that this works proportionally as well. Meaning, if I were to multiply any one of these sides by a constant, all of them get multiplied by that constant. So for example, I could go through and multiply 5s everywhere, right? So I know that 25, 20, and 15 would be related in a triangle. Or I could go through and I could multiply by 3s everywhere. This times 3 is 15, this times 3 is 12, that times 3 is 9. And that's kind of what tells me if the hypotenuse is 15 and one side is 9, then the remaining side must be 12. And I don't really have to calculate it, right? Because I think of this as 3 times 5, that is the 3 times 4, and that is the 3 times 3, and it's a 3, 4, 5 triangle. Right? So that's going to come in handy. There are sometimes in 205 where they'll give you huge numbers. They could give you numbers like 15,000 and 9,000. They don't expect you to sit there computing 15,000 squared and then subtracting 9,000 squared and then taking the square root of that. They expect you to realize, oh, it's a 3, 4, 5, right? They just multiply all the sides by 3,000, right? Another common type is the, who knows another common type? Not much bigger than those. Yeah?
Isn't there a 45, 45, 90?
Right. There's one where this is a 13. And what would the other two sides be?
9 and 12.
Huh?
9 and 12.
It's not 9 and 12. One side was a 12. There is a one with a 12. What would be the remaining side? Because you square this, you get 169. You square this, you get 144. You take 169 minus 144, what do you get? 25, which is the square of 5. Right, so the 5, 12, 13 triangle is also a very common one. This one is by far the most common though. More than likely on a final or a test, this is the relationship they're going to use. If they use any at all, they don't have to. But it's always one that you're looking out for, the 3, 4, 5 relationship. Right? So you realize that 9 is 3 times 3. This is actually 5 times 3. That must be 4 times 3. So that's in 12. Or you can find 15 squared, subtract 9 squared. But the numbers can get big where it's going that 3, 4, 5 relationship will be hidden, and time is of the essence on an exam. The quicker you can calculate something, the better. But this relationship is used all the time. I put that on the bonus point in the quiz. It was a 3, 4, 5 triangle. And on the test, the bonus point was also a 3, 4, 5 triangle. Okay, so now we know. So in part 6, I want to actually plug in everything. I didn't know everything though, so I went back to 4. Figure out that my y is 12. Now I know everything, so I'm going to come back to 6. And so I'm going to know that I have 2 times the x, which is 9, times the dx dt, which is minus 2, plus 2 times the y, which I now know is 12, times the y dt is equal to 0. It was plus. It was increasing, right? Yeah. So now, of course, I can divide both sides by 2. And so I have 12 dy dt is equal to minus 9 times 2. So dy dt is equal to minus 9 times 2 over 12. In which case, 2 into this goes 6. 3 into that goes 2. 3 into that goes 3. So I get minus 3 over 2. Now that negative tells you that the y is decreasing, which actually makes sense if you look at the picture. Right? As this gets longer, this is maintained the same. It has to slide down. So this must be decreasing. So you should actually get a negative answer. It's important that you recognize that. But this is a very typical kind of related rates problem. They're all going to follow this pattern. The only differences are going to be in the picture that you set up originally, and therefore the equation. So step 2 and step 4 will be different for every problem, but it's still the same process. So once you know that process, step 2 and 4 are the only things that you're going to kind of have to come up with on your own. But there will be common situations. You'll see triangles all the time. You might see circles, cylinders, boxes will show up sometimes, rectangles. Okay, so that was one scenario. So that's going through the 6 steps. And where are we? So the first time you're doing these, it might seem long and tedious, which it kind of is. It's one of the longer problems. Nowhere near as long as curve sketching, which we'll get to soon. And optimization problems tend to be a bit longer as well. But the good thing about related rates is it's always the same 6 steps. You're always going through these 6 steps in this order, right? So that makes it's kind of predictable in some way, which is comforting. Okay. Let's go back to example 1. It's the last example. We'll go through the rest in the next class, or most of the rest. I probably won't do all of it. Do some for you guys to practice. But let's actually do problem 1. But on a test, something like problem 3, or problem 4, problem 7, those are probably like the problems that I would put on the test. Maybe something like problem 2A, but I'd have to be in a particular mood to do that. Okay, let's do a problem 1. A right circular cylinder undergoes expansion. Its radius is increasing at a rate of 1 meter per second, while its height is increasing at a rate of 2 meters per second. At what rate is the volume changing when the radius is 1 meter and the length and the height is 3 meters? Right? So how do I know this is a related rates problem? They described the situation and they told me the rates. The rate of change of the radius is blah, rate of change of height is blah, and they asked me about another rate. At what rate is the volume changing? So I know it's a related rates problem. That's how they asked them, right? So tell you, this is going on, this is changing at this rate, that's changing at this rate, at what rate is this changing? Right? Whenever you see that kind of problem, it's a related rates problem. It means that you go into related rates mode, you do these 6 steps in that order. Okay, so step 1, we read, so we understand the situation. Step 2, you draw a diagram. Now this diagram doesn't really help us, really, except to like kind of jog your memory, because you've probably drawn a lot of cylinders back in high school. So that would be the radius, and that would be the height. So that's our diagram. Now it says it's expanding, right? And it says that both the radius is changing and the height is changing, which is why I labeled this by R and that by H. It didn't have to be that way. They could have just said, oh, just the radius is expanding, but the height is staying the same, in which case I would label this with a constant. Right? So you really want to read to see who's a variable, who's a constant. Okay. So 3, we're going to write down what do we know, what do we want. So what do we know here? Things are expanding. So we know that the radius is changing, dr dt. We actually know a value for that. That is 1, right? It's increasing at a rate of 1. They also told us how the height is changing, so we know dh dt. That's increasing at a rate of 2. What do we want? How fast is the volume changing? Let's define it to be dv dt, which you don't really see in this diagram, but we'll figure it out. And we want dv dt when they told us, when the radius is 1 and the height is 3. When r equals 1 and h equals 3. Write the problem carefully that describes the situation. I know the cylinder is this. I know that's what I know. This is what I want.
No zero.
And so we get to step 4. Now the moment we draw this picture, it all comes rushing back and we go back to high school geometry. I don't want to go back. I don't want to go back. Right? And then remember, oh yeah, that was the formula. What's the formula for the volume of a cylinder? R squared h. See the nightmares again. Okay. So that's going to be the thing that relates all our variables. That's going to relate r, h, and the v. Right? So everything from step 2 and step 3, I can relate in this one equation. Right? And so now, this leads us to step 5. I'm going to differentiate with respect to t. Derivative of v with respect to t is just dv dt. Then I'm going to differentiate this with respect to t. How do I do that? Product rule, right? There are two functions here. Don't forget your old derivative rules, right? R is a function of t and h is a function of t. I need the product rule. So differential derivative of this is 2 pi r h times dr dt, because I just differentiated the r function, plus pi r squared, derivative of h is 1, but then I multiply by dh dt, because I just differentiate the h function. So that's going to be my equation. Now I go to step 6. I'm going to plug in what I know and solve for what I want to find. I know r, I know h, I know dr dt, I know r, I know dh dt. I know everything. I actually know everything at this point. So now I just plug in. I don't even need to go back here because I know everything. So 2 pi, my r, I want it to be 1. My h, I want it to be 3. My dr dt is 1. My r is 1. And my dh dt is 2. So here I get 6 pi plus 2 pi. So this is 8 pi. The volume is increasing at 8 pi, and technically it's volume, so it's meters cubed per second, but I don't care about the units. 8 pi would be the acceptable limit. So that's that problem. So again, related rates, how do I know? They told me about some rates, and they asked me to find another one. What we do is we read the problem very carefully. That helps us to set up a diagram if we need one. Right now we know what we want. This diagram is going to kind of jog our memory about what formula we want to use. So things like Pythagoras Theorem, volume of a cylinder, area of a rectangle. Like a lot of geometry formulas are going to come up here, right? So those you have to remember. Once you have that, it's just differentiating with respect to t, plugging in what you know. If you know everything, great. If there's something here that you don't know, go back to step 4, figure out what it is, come back here and plug it in, and then you answer the question. So we'll stop there. We'll pick up with this on Wednesday, and yeah, we'll move from there. Oh, I have to give you back your test. So remember, look these over, and then see me either tomorrow or Wednesday, because Thursday is the last day to draw.